If a charged particle Q moves through both an electric and magnetic field, the total force acting upon it is known as the Lorentz force, given by this top equation here. However, since we're doing a simplified DC motor, this term here, accounting for an electric field, can effectively go to zero, and we'll simplify to this equation here. This equation takes account the charged particle, its velocity vector, and the flux density of the permanent magnet. This drawing here is a simplified model of what we have as for a physical setup. We have a power source here, with the electrons coming out of the positive end and passing into the copper wire at points here. It's then going to be flowing around the coil here and interacting with the magnetic field coming up. With the current moving this way and the magnetic field going up, we are going to have a resultant force coming out of the page here, causing the wire to spin around these points here. So here we have our simple DC motor, with the power supply coming from 4 AA's, current flowing it out from the red wire up into the post, into our makeshift electromagnet, and out to the side and back to the battery, with our permanent magnet here on the bottom supplying the magnetic field. So let's trace the current and see how it creates a force using the right hand rule. The current is going to the right as denoted by our thumb. The magnetic field is going up as denoted by the fingers, and thus the force will be coming out of the palm here. And so the top of the wire will be forced this way. We can reverse that with the current flowing the opposite direction on the bottom. So if we go ahead and give it a little spin, and it starts right up. As mentioned before, this part of the spinning is caused because of the magnetic field coming up from the magnet here on the bottom. However, if we were to introduce another magnetic field from, say, a stronger magnet, such as this Earth magnet with the North Pole denoted by this black tape, we will see we can actually get the motor to stop and change directions because this field is stronger. And we can get the motor to go back and forth then. Here we have a coil with very few turns. Here we can see it runs fairly well, just fine. However, the electromagnetic field created by this few number of turns isn't nearly as strong as, say, something with 9 to 10 turns and significantly thicker. Thus, using the wire with more turns, we are actually going to generate more power. Here we have the motor running with about 6 applied volts. We will compare this to a speed of a battery running only about 1.5 volts. With the AA batteries removed and a single D-cell battery underneath here connecting to these two terminals, we only have 1.5 volts flowing through it now. And thus the magnetic field strength is significantly less, and while the motor is still spinning very quickly, it does have less power.